Hello.
Okay, Dave. Dave. Dave got a new system and we tested it just before we started, but there sounds like there's something went wrong with it.
Hello.
Hey, Dave.
Hello.
Hello?
Hello.
Hi, Dave.
Hi, Rick. Sorry, I
Yep,
lost
we
you
can
for a
hear you.
minute. Okay, I lost you for a minute there.
Yeah,
Okay. Am I
ready to
ready
go.
to go?
Yep.
Okay, sorry about that. Hi, everyone. I want to thank Rick for the introduction that I did not hear. And I want to thank Jeremy Pittman, who extended the original invitation for me to do this. And just let me know if at any point you don't understand or don't get the proper audio or video, because I've never done actually a webinar before. So I thought I'd talk about some work we're doing on climate change and impacts on prairie water supply, but with an emphasis on the uncertainty in our capacity to predict what's going to happen with changes in runoff and water supply. And a lot of that uncertainty is directly the result of the incredible complexity of the climate system. And so here's an illustration of the global climate system in all its complexity and nonlinear and chaotic behavior. A lot of that chaotic behavior is the result of all the interactions between all the components of the climate system, and in particular some major positive feedbacks whereby the forcing gets amplified. So, for example, models indicate that given an increase or a doubling in CO2 concentrations in the atmosphere, there would be only a 1 degree increase in global temperature in the absence of feedback. But that 1 degree forcing is very much amplified by positive feedbacks in the climate system. And of course, a major part of the climate system is the hydrology. In fact, you could argue that at least over land, the major part of the climate system is hydrological. So these hydrological processes are embedded in climate models. At the global scale, given the coarse resolution of global climate models, there is relatively simple modeling of the global hydrological system. But with scaling down to the regional scale, with dynamical downscaling to regional scales, there is more sophisticated modeling of the hydrological cycle. And in fact, the Canadian regional climate model and the Canadian Earth System model contain the CLAS Canadian Land Surface Scheme. And here's an illustration of it. And you can see that there are hydrological, a major part of that, of CLAS is a hydrological module whereby there is the modeling of interception and seepage and even leaf drip and through flow through the vegetation. There's a snow component. There are 3 soil layers and the infiltration and seepage of water between these layers, and eventually the seepage to the groundwater zone. So we thought, if there is hydrological modeling embedded in the Canadian model and in other regional climate models, let's extract the runoff data. Let's extract the variables which relate to runoff, and see how well they actually simulate the hydrology on the prairies, with a focus on the South Saskatchewan River Basin. The red dots represent the RCM grid, so relatively high resolution of 25 kilometers across southern Alberta, as opposed to the GCM grid, which is 250 or 2.5 degrees by 2.5 degrees. So we're dealing, by working with RCMs, we're working with much more detailed and higher resolution data. For the Bow River Basin, the hydrograph, the recorded runoff, I think this would be a Bassano probably, is in blue, and the output from class within the Canadian Regional Climate Model is in red. This is the raw runoff output. Runoff, this is not stream flow. There's no routing mechanism. This is simply runoff in millimeters per day, watershed runoff, and it's in red. And you can see that the simulation is actually fairly good in months 4 through 7. The spring runoff. On the other hand, the low flows are underestimated. So during the low flow seasons of late summer through fall and winter, there is an underestimation of the model of the runoff of the Bow River Basin. Well, we corrected for that because it's a systematic bias. We corrected for it, and so in green is the model, the bias-corrected model simulation for the 20th century. And we apply this bias correction to all of the output from the model, including the future scenarios. And so this plot is a comparison of the 20th century modeling of runoff in the Bow River Basin as opposed to 21st century runoff, pink. Don't ask me why we choose pink, but you can see the contrast between the simulation of the historical runoff in green and the simulation of the future runoff, and the difference being that there is higher runoff in winter, there is higher peak runoff, and then lower runoff in the summer. That's the major discrepancy between the historical and the future runoff. That's the major change as simulated by class within the regional climate model. Now, the big advantage of taking this approach is that the modeling of climate and hydrology are coupled. As the climate changes through time, so does the hydrology. And so the most useful information that we extracted using this approach were these time series, where in blue we have the historical simulation of the runoff in the Bow River Basin, the solid blue being the bias corrected, and the recorded flow being represented in black. And then on the right side of the time series is the projected for future flow of the Bow River for the period 2041 to 2070, where red is the bias corrected data. Now, if you were to compare the means for these 30-year periods, there's not too much change. What's most dramatic is the change in the variability, that there is quite a large increase in the difference between the lowest flows and the highest flows in the Bow River Basin. And that's the value of this coupled modeling of the hydrology and the climate, is you can extract information, you can derive information on the variability, interannual variability in the flow as the hydrology and climate evolve together in this simulation. So this is just the Canadian model. Here are the same results, but for 10 models, 10 regional climate models. And once again, you can see in the future the huge, quite dramatic increase in the range of flows simulated by these models in the future as opposed to the recent past. Janine Saint-Jacques, some of you may know, she was our research associate, first of all a postdoc and then a research associate here at Park for 9 years. And in January, she assumed a new position as an assistant professor at Concordia University. So Janine took the lead on this project, and we've submitted a paper for publication. Okay, I want you to compare these simulations to some work we're doing where the hydrological modeling is being done by our colleagues, Stefan Kinzel, Monterey Ferramarzi at the U of A, Brian McDonald, who works for Alberta WaterSmart. And so they each have their favorite fully distributed dynamic hydrological model, and they spent a lot of time calibrating and validating these models using a large spatial database for the Oldman Basin, all the basins in Alberta in the case of the project at the U of A, the Athabasca Basin in the case of WaterSmart's work in the North South. And our role is to supply the climate information. And I've indicated who's supporting this work. So to give you an example, this is the work working with Steph at the U of L. And for the Castle Subbasin in the Oldman River Basin, southwestern Alberta, he has plotted the historical simulation, the ACRU model run using historical weather data for 4 30-year periods overlapping. And you can see, if you follow those thinner colored lines, you can see that as we move from 1961 up to 2010, the hydrograph shifts to the left, such that there is more winter flow and less summer flow. And that historical trend continues into the future. Steph took regional climate model that we gave to him, RCM data, for 2 scenarios, a cool and wet scenario in black and a warm and dry scenario in red. And so the future scenarios are those bold curves, and they also indicate higher flows in winter, especially with a warmer climate, but on the cool side of the projection. So by cool, we don't mean it's global cooling. It just means that it's the least amount of warming projected by these models. And it's also the wettest scenario, and therefore you can see much higher flows in wintertime, but lower flows in summer. And that same scenario applies to the warm, dry hydrograph, but not to quite the same extent. Okay, so really interesting and useful work. But this is offline hydrological modeling. What I mean by that, it's not coupled. We extract the climate data from the models, we give it to Steph, and then he reruns his model using a change in climate. This is really by far the most common and the conventional way to approach the issue of climate change and water. And in fact, it is standard practice in hydrological engineering. So here we have a scatter diagram where we plotted the 10 regional climate models in terms of the temperature change and the precipitation change that's projected from the recent past into the future. And Steph said, well, I don't want to run my model for all 10 scenarios. Give me 2 of them. So we actually gave him a median scenario in green that's close to the medium climate change. And then we gave him 2 extreme scenarios. And he ran his model using those 2 extremes. And like I said, this is the kind of approach that's used repeatedly and is recommended, in this case, recommended by a consulting firm that was contracted in Ontario. They were contracted by the Ontario Ministry of Natural Resources to produce this large report, produce guidelines for the assessment of the hydrologic effects of climate change. And that's exactly what they recommended, that you take the climate change projected by a subset of models and then apply it to your favorite hydrological model. And here's an example of some of the results they obtained. This is a hydrograph that's time series. The annual flow for the years 1961 to 1990 in black, the recorded flows. and then the simulated flows for the future in those gray curves. And you can see that most of the models project higher flows. A few models project lower flows. So that's good to know. It's good to know you can expect more water in this particular basin. There are higher water yields. But I want you to notice how those future hydrographs replicate the historical ones. So they haven't modeled any kind of change in climate variability. They've simply taken the climate changes, the changes in temperature and precipitation projected by the models, apply them to their hydrological model, and therefore they either get more flow or less flow.
I would suggest that's the limitation, even though it's a very common practice and produces extremely useful information. The limitation is that the climate variability is inherited from the calibration, the model calibration. And also, there is a subset of models. In this case, to their credit, they've used, I think, 8 models. However, there are many, many global climate models and many runs of many global climate models. And so here we have each one of those colored triangles is a run of a global climate model for the Canadian prairies. And the projections of changes in temperature and changes in precipitation in winter and summer. So you can see we can expect by the middle of this century in winter that the temperature has risen anywhere between 1 and 6 degrees, and that there's quite a bit more precipitation, up to 25% more precipitation in winter. So a warmer, wetter winter. In summer, the increase in temperature is not as large. It's as much as 4 degrees. And more importantly, the increase in precipitation is at most 10 to 15%. In fact, about a third of the models project less precipitation. So summer is not warming as much as winter. And that amount of increase in precipitation is unlikely to offset the increased evapotranspiration. So we can expect warmer summers and possibly either not much change in soil moisture or more likely drier conditions. Okay, but the point I want to make is not what we can expect in terms of average climate, but the huge scatter of points. Now, to some extent, this is because it's different models, but notice that even a model, a model indicated by the same color, there's a scatter of points. It's the same model. Now, there are different assumptions about different initial conditions and different assumptions about greenhouse gas emissions, but it's still the same model. Now, given this plethora of data, understandably, most hydrologists will only choose a few of these projections to capture the range. But here's a study from Colorado where Harding and his colleagues took output from 112 models. So for different greenhouse gas emission scenarios, B1, A1B, A2, and for different models, here is the spaghetti. This is a large number of time series, each one corresponding to a different run of a different model. And when they took these 112 climate projections and ran their hydrological model, here is the projected flow of the upper Colorado River. You can see that, well, the mean is a gradual decline in flow, but the actual projection ranges anywhere between quite a significant decrease in flow right up to a significant increase in flow and everything in between. Here's a couple quotes from this paper. They concluded that any kind of hydrological study that relies on one or a few climate scenarios is unacceptable because it's influenced by which projection was chosen. And they noted that global climate models differ a lot in terms of, especially in terms of how they simulate decadal climate variability. Remember that. And furthermore, they concluded that it is the unforced, it's the internal variability. By forced, we mean forced externally by greenhouse gas emissions or by solar activity, but the internal unforced variability is probably the largest source of uncertainty. But for any climate projection, the corresponding change in stream flow is dominated by a random or chaotic component. Here are some other studies that have looked at the uncertainty in projecting future climate. The first group from Europe saying that even though there's been a substantial increase in computational capacity, in CPU, and substantial model development, the spread of models hasn't changed. And they were saying that this uncertainty is basically irreducible because of the internal variability of the climate system. Fisher, another group of Europeans, saying more or less the same thing, that the uncertainty is owing to internal variability and is essentially irreducible. And therefore, they say it's not really possible to give decision makers what they want. They want information on local change. They want information on extremes. Because as you people know, it's much more challenging to plan and manage for drought and flooding than for a gradual change in the average. And Fisher said we actually can't tell people what to expect in terms of drought and flooding because of the large amount of internal variability, which these models have difficulty simulating. And then coming over to North America, Claire Desser and her group from Boulder, Colorado, saying that once again, it's natural climate variability that's the problem that poses inherent limits on our capacity to predict, and especially in winter, and especially at middle and high latitudes. Well, that would be us, because of course, most of our water is derived by snowmelt. And so let's look at how the Canadian Global Climate Model simulates winter precipitation in Saskatchewan. Another scatter plot, and instead of hundreds of models, we have one model, and we have just two different greenhouse gas emission scenarios, A2 and A1B, and this is winter time, and it's change in precipitation on the horizontal axis and change in temperature on the vertical axis. Now I want you to note that with the exception of that outlier in the upper right-hand corner, that the simulations don't really separate according to greenhouse gas emission scenario. They overlap. And so it doesn't matter really which greenhouse gas emission scenario you choose, there's the same amount of uncertainty. There's the same spread. And also, if you choose only one of these emission scenarios, so let's take the A1B, and so if you look only at the dots that are labeled in purple, labeled A1B, this is a single greenhouse gas emission scenario, and it's a single model. It's the same model run 5 times, and yet we get 5 future climates. And the only difference is when they ran the model, when they spun up the model, they made a slight revision in the initial conditions. It's a very small perturbation. In fact, one of the modelers said it's like dropping a pebble in the Pacific Ocean, running the model again, and you get a different future climate. Just another indication that the largest source of uncertainty isn't necessarily differences between models or differences in greenhouse gas emission scenarios. It's the internal variability of the climate system. Another way of showing that, of hammering home this argument, is a plot from the IPCC recent 5th assessment report, where this is a plot of the fraction of the total variance, basically the uncertainty over time through the 21st century, attributable to differences between models in blue, attributable to the greenhouse gas emission scenario in green, and the internal variability in orange. And you can see that actually, in terms of precipitation, it doesn't matter too much what you assume about greenhouse gas emissions. That it's the differences in the models, but more so later in the century. For the next few decades, the dominant factor is just the internal variability of the climate system that's going to dictate our future climate. So, in our lab here at Park, most of our research is on internal variability of the climate system by using tree rings. So you see some trees here. There's some trees in the bottom right-hand corner. We don't use those trees. We use the trees that are up on the side of the hill that are more sensitive to the hydrological cycle. But there is obviously the tree growth depends on the soil moisture, but there's a high correlation between soil moisture, runoff, and water levels in the watershed. So we've collected more than 6,000 pieces of old wood. They're stored in the basement in this concrete bunker where we drag the wood in from the field, and I hire students to use our DeWalt power tools to cut and plane and sand and polish the wood until the tree rings are clearly visible. Across the bottom here we have a few years of growth of some old Douglas fir in the foothills, eastern slopes of the Rocky Mountains. And throughout most of the prairies and at low elevation in the mountains, the limiting factor on tree growth is moisture. The trees have plenty of heat in the growing season. They have good soil, they have nutrients, they have lots of sunlight on the prairies, and increasingly more carbon dioxide. So all of their growth requirements are met, except in some years, in most years, the amount of soil moisture, the wetness of the watershed limits the tree growth. So this is where we've been collecting wood for 25 years. Each one of those triangles, about 200 locations, all the way from down in Montana, right up to the end of tree growth in the NWT, but mostly on the eastern slopes of the Rockies, because that's where most people in Saskatchewan and Alberta, and even a few people in Manitoba, get their water. And so for the Bow River Basin, we have tree ring models. We have reconstructions of the flow of the basin that explain 80%, more than 80% of the gauge record. This is a model based on trees that go back to the year 1525. The shared variance between the trees and the gauge is more than 80%. So we're able to reconstruct the flow of the South Saskatchewan River back to the year 1110, 900 years of annual flows. And the way that this time series is plotted is above average flows in blue and below average flows in red. And so you can see that there have been times when the flow of the Bow River, or the South Saskatchewan River, the Old Man, has been low for decades and almost a century in the case of the 14 and 1500s. And so the take-home message here is that those of us who have been on the prairies for only at most 120 years have not seen the worst-case scenario in terms of the duration and magnitude of drought. The other take-home message here is the natural variability. If you squint, you'll see blocks of blue and blocks of red, because this is the decadal climatic variability that characterizes our climate. We can demonstrate that when we take the same data and transform it to a wavelet transformation. And so the length of the cycle is on the vertical axis. And over this time series, you'll see some, in red, some indication that there are decadal length cycles that are stronger in some centuries than other, but throughout the tree ring record, there's an indication of this decadal scale variability. And people are discovering, everybody seems to be discovering what paleohydrologists have known for decades, is that this decadal climatic variability is an important component of our climate system in the West and needs to be acknowledged because, for example, this workshop held recently and this report produced by the US National Academy of Science points out that what we've known for quite a few years is that the hydrology and the probability of flooding and drought is quite different depending on the decade or several decades and the status of the Pacific Ocean, the circulation of the Pacific Ocean. So PhD student here, Sanu Gurapu, who's a PhD student here at Park, has a paper that came out recently where he demonstrated that there are different flood frequency curves depending on the status or phase of the Pacific Decadal Oscillation. And these flood frequency curves are completely, in the case of the North Saskatchewan River, they don't even overlap, not even the confidence bands overlap. So whereas conventional hydrological and engineering practice is to produce a single flood frequency curve for a gauge, in fact, there are two different flood frequency curves depending on the phase of the PDO. And the other reason to acknowledge decadal climatic variability is you can be misled in terms of trends. So this next diagram produced by NRCan shows within that blue box, if you have a gauge record that's less than about 40 or 50 years, you haven't spanned an entire low frequency cycle. So there's a lot of gauge records that are post-Second World War, and you can be led to believe that there is a declining trend in stream flow shown in yellow, but what it really is 1/2 of a cycle. So ideally, before you establish what the trends are in stream flow or water level, you want a gauge record that's long enough that it encompasses at least one or more cycles of the PDO, which is the case for the South Saskatchewan River at Medicine Hat. The record goes back, the gauge record goes back to, actually back to 1913. This is naturalized flow. This is from Alberta Environment and the reconstruction of the naturalized flow. And you can see the decadal scale variability. You can see that there are decades or a few decades in which flows remain consistently low, and then other decades or a couple decades in which flows are relatively high. But because this gauge record spans a couple cycles of the PDO, we have more confidence in that long declining trend in the flow of the South Saskatchewan River. So I'm going to try to summarize in the last 5 to 10 minutes. And doing that with this idealized decadal cycle, the PDO cycle. And of course, it's a perfect sine wave, it's idealized. And then the annual cycle, or on the order of years, which is El Nino, La Nina, where in the West, we tend to have wet conditions during the La Nina and dry conditions during El Nino. And then the trend, the long-term trend, which has been attributed to global warming. Well, our climate and hydrology are a combination of all three of these modes of variability: the trend, the high frequency, and the low frequency. And when you combine the three, you can see them expressed in a gauge or water level record. So what do? Given all this uncertainty, given the fact that the climate models have difficulty simulating the natural variability, and we want to avoid being vulnerable to climate change, and so this little cartoon shows that you don't want to be the community or the person or the organization or the company in the lower part where you're complacent, you're moving along. There are ups and downs. There are these troughs and peaks in the water and the economy. But you're pretty resilient, and you live in Canada. We have lots of money. We have lots of resources. We have relatively good government, and so on. And so you're doing okay. But then you get zapped. You get zapped by a shock, which is a major flood or a huge drought or a dramatic shift in climate. And if you're not prepared, you're vulnerable and you're toast. It's game over. You've fallen off the cliff. But if you're the upper person or company or government or community, you're happily, merrily trucking along through the ups and downs that we experience, and you get this big shock, this long, severe drought, but you're prepared. And so you're able to recover. Your company or your community is resilient, and you recover and rebound And so that's the ideal scenario, socially and economically, is where we are prepared for these climate shocks, and we've done some planned proactive adaptation. So I'm going to give you some examples of how a few of our funding agency, a few of our clients are using our information to prepare for these shocks. Here is a study we've just completed, funded by the Alberta government and co-sponsored by the City of Calgary and EPCOR, where we gave them, for the South Saskatchewan and North Saskatchewan rivers, our treating reconstructions, but downscaled to weekly flows. So we gave them 900 years of weekly flows of the South and North Saskatchewan rivers. You probably want to know how we did this. Well, I was working with Nessa Illich Optimal Solutions, his company in Calgary. Nessa wrote an algorithm. He wrote a script to stochastically downscale the estimates from the tree rings to weekly flows based on the PDF, based on the historical flows from the gauge record, but then also accounting for the distribution of flows and the decadal climatic variability contained in the treating record. Okay, so the conventional approach to stochastic hydrology is to use the gauge record, but Nessa incorporated and constrained his model using the variability contained in the treating record. And so you can imagine if you have 900 years of weekly flows, there's some pretty interesting things you can do. For the City of Calgary, we've taken their drought management plan and the 6 seasons that they define and the 6 periods of water restrictions that they define within their drought management plan. And so instead of a single flow duration curve for the year, we have 6 flow duration curves. And we have a flow duration curve using the gauge record in blue and a flow duration curve for each season using the 900 years of weekly flows. And as you might expect, the red flow duration curve captures a lot more low flow. And if you take just one of the seasons, season 3, the summer season, the trigger, the flow trigger defined by the city is that dashed line. So at that flow, some kind of water restriction comes into place. You can see that the gauge record never gets that low, but there's a bunch of years in which, in the 900-year record, that critical threshold would have been exceeded. Sunil also has produced SDF curves for the prehistoric 900-year record versus the historic record, so you can compare that how representative is really the gauge record, even though it's a 100-year gauge record. How well does it represent conditions over a period of 900 years? EPCOR, this is a presentation given by Steph Neufeld, who some of you may know. She works for EPCOR, and she gave a presentation last fall that I found interesting because she used our work, acknowledged our work. I didn't put that in there, work by Gabe Sachin, she did. And so here is that 900-year record. And then Steph posed some questions, really, how low can the river get? And so she teased out the maximum, the average, and minimum weekly flows from this 900-year record and said, you know what? The North Sask could get as low, according to this information, as 10 cumecs. At that point, the river is likely to be a series of disconnected pools. And in fact, Fort Edmonton's been around for a long time, and when in the 1796, I think it was, the journals from Fort Edmonton said that they had to stockpile the furs because they couldn't move the furs. A canoe couldn't get down the river. So it was probably this situation where the river had been reduced to a series of disconnected pools, and so they couldn't move the furs. Another question, what does a long drought look like? Well, she used the drought of 1714 to 1718, which in the tree records keeps showing up as a severe, really severe period of 5 or 6 years of low flows. And so she plotted the flows according to our reconstruction in blue, and then she adjusted the flows because there were 2 dams on the river, the Bighorn and the Brazeau Dam upstream of Edmonton. And so this indicates how those dams, if they had existed a couple of 100 years ago, would have mitigated the impacts of that drought. Or more interesting scenario is when this drought reoccurs in the future, how effective will the dams be in mitigating the impact of that drought? The only difference is, of course, the climate now is quite a bit warmer than it was back in the early 1700s. So when that drought reoccurs, it'll be in a warming climate, and it will reoccur at some point. And then finally, a couple more slides. This is a different company. This is Teck Frontier Resources, a fairly major player in the oil sands. It's a big resource company. We have a reconstruction of the flow of the Athabasca River. And when we published that, Teck gave me a call and said, we need to talk. Would you get on an airplane and fly to Calgary as soon as possible? So I went to Calgary the next day and went to their boardroom. Didn't know what to expect. And they said, we'd like to use your tree rings to inform the future stages of a proposed oil sands mining project. Well, that's kind of cool. So I Googled Teck and oil sands, and according to the Globe and Mail, they're planning to build a mega mine that's going to cost $20.6 billion and produce 260,000 barrels of oil a day. And they want to use tree rings to, I mean, it's going to be, not to be modest about this, it's going to be a tiny part of the science that informs the construction and operation of this mine. But they have contracted Golder to use our tree rings. And Golder gave a presentation last fall. And just one of the slides from that presentation looked like this, where the Golder has given Teck a water supply probability exceedance water supply scenarios. And there's 5 scenarios. There's based just on the gauge record on the Athabasca River at Athabasca. It goes back to 1958. And then they did some stochastic hydrology and produced 3,000 simulations. In black is a couple of climate change scenarios. And in the middle, in brown, is the tree rings. And that inset, that inset diagram is just the higher probabilities expanded, and you can see that there's those 5 water supply scenarios, and tree rings is one of them. Okay, I'm going to stop here, give a few minutes if there's any questions, but that basically is what we've been up to for the last few years.
Yeah, thank you, Dave. Audience,
Somebody still there?
Interested? I think I am.
Hello?
Hello. Audience, please type in any questions.
Hello?
I can hear you, Dave. You can't hear me. And I don't know why. Hello? Hey, Dave. Your screen is still showing. Hi, Dave. Okay, we have.
Well,
Will the data set be publicly available? And my answer is
hello.
Dave, your earphone's not working.
Hello, Rick.
Yes.
So that entire presentation didn't happen?
Yes, it did.
Oh, the presentation happened.
I'm sorry, is this Dave?
It's Dave, yeah, Dave speaking.
Sarah says can't hear you to Dave, but we can hear Dave.
Okay,
And now you can hear me.
I can hear you, yeah.
There's a question, will the data set be publicly available
Which data set?
that you've been using?
Well, it's all university-based research, so it's all in the public domain. We've been using a bunch of data sets from
Okay.
climate models and some tree rings and so on, so it depends on where they can get it, depends on the data set, but yeah, it's all in the public domain.
Okay. So Streamflow data set is available through various places. And Art says he can hear both of us now.
Good. Now, did everybody hear the presentation?
I believe so. I heard it all.
Okay, good. I was afraid I was just talking to myself for the last 45 minutes.
And Art says yes.
Good, good.
And anybody else have a question? Sarah said the problem may be with my microphone because she couldn't hear me speaking to Dave, but
yeah, I can't figure out why my microphone just cut out there a couple times.
okay.
Yeah, gonna have to figure that out.
Maybe I've got a short because now you can hear me. While I've got you on the line, could you send me a copy of the PDFs, please?
You bet.
Okay, as we post them to those who attended, make them available. If they want to download them, they can.
Okay, so a
We have
PDF.
a good question.
Good.
The question is, one of your slides compared a 30-year historic record to a 30-year future scenario. Have you compared the variability of the entire historic record to the scenario?
Now, I think there was a couple slides where we did that. And, I think I understand the question. Whether the model, what kind of performance, or how do we evaluate the performance of the climate model in terms of how well it simulates the historical variability? And
Right.
yes, we've done that. In the case of temperature, it's actually very good. In the case of precipitation, it's not nearly as good, but this is typical of climate modeling in general, is
Right.
that the climate models have much more difficulty simulating precipitation, especially in summer, than they do temperature. But after all, temperature depends primarily on the global energy balance, the thermodynamics, whereas precipitation depends very much on the circulation of the atmosphere and the ocean and the dynamics of the climate system. So all models have more difficulty simulating precipitation.
Okay. Do you have a favorite climate model? Not climate model, precipitation runoff model yourself?
Nope. I'm democratic about that because I work with a bunch of hydrologists, and so I tend not to favor one model over another. So I tend to remain impartial because I'm working with people that use a variety of hydrological models, and we just give them the climate data they ask.
Okay. Okay. Wait, here we are. Bob says, actually, I was thinking that the 1970-2000 record was mostly a warm phase PDO situation and wondered if the inherent variability was roughly similar for both warm phase and cold phase.
That's a really good question, and I can't answer it. We'd have to look more closely at the data. I can't answer that question off the top of my head. But
okay, the questioner was Bob Halliday.
Yeah.
So if you can.
Bob, tough Bob to ask a good question like that.
And the hard ones, yes.
Yeah, ask a hard question. What we have looked at is the probability of drought during the wet phase of the PDO is practically zero, and we're talking about a significant drought. And,
okay.
But the probability of flooding is actually an excess water source high. So that's mostly what we look at.
Okay. Okay. Let everybody know that a follow-up email containing a link to download the PDF file of today's slides will be distributed to all registrants in the coming days, shortly after Dave sends it to me. As always, we appreciate your feedback. Note the next webinar is Thursday, April 20th, Manitoba, Wetland Vegetation and Urban Runoff. Chris Penner will be the presenter, and make sure to get your name in for notice of future events. Join CWRA, cwra.org, and join as a new member. If your membership has expired more than 30 days ago, you need to join as a new member. To receive notice for future events, that'll happen once you're a member. This time, CWRA would like to thank Dave Soshen and Park for their time and contribution, and thank you to everyone for attending today. Thank you all, and we need to adjourn because we have another meeting starting in 4 minutes. Thank you all, and thank you very much, Dave.
Thank you, Rick. Bye now.
Bye now. See you on the next call, Sarah.